There we go.
So, this week we are going to talk about a lighter weight topic than what we normally do. At least, you know, we're not getting into like the heaviness of classes and inheritance and all of that. Today, this week, we're going to be talking about exception handling, and we'll be talking about debugging. Right? So, please load up a console app, C# console app. There we go. We will get underway. So it's very probable that you remember the word exception from the programming that you've been doing so far. Certainly in Unity you will have experienced probably a fair number of things like null reference exceptions. So an exception is an error, but it's a specific type of error. It's a runtime error as opposed to a compile time error, right? So when we have a program, my markers in the last classroom. How unfortunate. So, does this work? It does. Good. So when we have a program, it's useful to go through the stages that take place converting the programming code that we write to the executable code that the computer executes, right? So the first thing that we have is our programming source code, right? So step one is source code. The program, in our case, of course, C#, right? C# in our case. So we all should have some idea that there is a process or program called the compiler, which takes the program in and executes it, right? But this is actually not quite true. So you have compilation. That is the process of taking source code and turning it into what we call machine code. So, machine code. Machine code is then the thing that is executed. Execution, right? In a Windows style environment, you will typically know that something is an executable file because it will say file.exe. Right? So the .exe file extension says this is executable, right? There you go. Now, this is somewhat unique to Windows environments. In more Unix-based environments, that's just a flag that you set on the file, whether it's executable or not. Many different file types can be executable, not just .exe. So let's dig into this a little bit further, right? Let's discuss what the individual stages of compilation are, right? So during the compilation process, source code undergoes a number of steps. The first step is called pre-processing. And it just so happens that I did my PhD in this kind of stuff. So you have it from the horse's mouth. So pre-processing is a step whereby certain symbols that are used inside of your program are converted to other symbols which are more interpretable to the machine. For example, variable names. So when we write a program, we say int x, y, etc. We give them names which are, useful to us as program members, as human beings. The computer does not care for, read, or interpret these strings as meaningful names. During pre-processing, these variable names are exchanged for an internal representation. It's an internal representation for memory addresses, right? So it's like, memory address 1, memory address 2, etc., right? It gives them a number because it knows how to work with numbers, right? Pre-processing does other things as well, but we don't have to get too heavily into it. In a language like C#, which has static type checking, the reason it's called static type checking is because it is done up front before execution. Yes?
Is the machine code something
It is actually its own language. It's not the same thing as assembly code. So assembly code is another form of source code which must be compiled into machine code. The thing that makes assembly code is that the transition, like the compiler, is not doing nearly as much, right? The language is already very, very close to machine code. So when you're programming in an assembly language, you are, okay, let me back up a little bit, right? Your CPU, right? Here's the structure of your CPU, right? Your CPU has a few different regions. You have some register memory, a small memory unit embedded in the CPU. You have a control unit. The control unit is what reads the instructions, right? And then you have a big thing, which is most of the CPU actually, called the arithmetic logic unit, or ALU. This is the circuitry that actually performs the mathematical and logical operations, right? So when you ask to add two numbers, there's a little piece of circuitry inside the ALU that performs add, takes two things out, produces produces the sum of those two things as its output. That gets wired back into the register selected by the instruction, right? So, whereas in assembly language, you would say something like, and I don't know if I can even use this one. Let me try this one. That's better. In assembly code, you might have something like add R3, R2. R3, R2, R1, which is take the value in R2 and R1, add them, and then place it in R3, RB registers, right? So it's fine, it's good instruction. Machine code would substitute each of these symbols for the sequence of ones and zeros that open the gates in the circuitry, right? So this translated to machine code looks like, 1, 0, 1, 1, 1, 1, 0, which would correspond to add, right? Then you have like 0, 0, 0, 1, 1, or, that would correspond to register 3, 0, 0, 1, 0, that would be 2, 0, 0, 0, 1, that would be register 1, right? So the actual machine code itself is binary encoded and almost completely no human, it's almost beyond human capability to read and understand that, at least quickly enough to be able to usefully program it. That's why the assembly language exists, right? Now, back in the day, when you were programming your computers on punch cards, that's what you had to work with, right? Now, we're talking about like maybe way back in the 50s and 60s. This is how you program a computer. You had to program it in binary code, right? You move forward a few years, right? People have a couple of very interesting, they have a few interesting takes on how to better design a computer. One is to take instrument, they're quite loud out there, I think. Excuse me, we're going to have to laugh. So, what was he saying? Something about 60s? Yes. So, there was this interesting piece of electrical equipment that was at the time used to measure, electrical impulses, called a cathode ray tube, right? The cathode ray tube is basically a photosensitive screen sitting on top of an electron stream where the electrons are deflected by magnetic plates, right? Therefore, you can direct it to different points on the screen, right? So, and that's why it's called a screen, because it's screening electrons, right? So, somebody had the bright idea of hooking that up to a computer. Suddenly, computers have display, right? Somebody had the bright idea of taking an electric typewriter, hooking that up to a computer. Suddenly, you can enter commands using a keyboard rather than on punch cards, right? Once you have those two key innovations, you can compose text, right? Once you can compose text, you can write a program in text. That plus having permanent memory storage. That's another thing that computers originally didn't have. A computer was just here is my input. That is all the memory. That is all of the memory. I crunch it. I produce an output. I keep no record of what I've done. That was the original computers. They were very single task oriented, right? Once you have memory, monitors and keyboards, you are able to compose files, right? Once you have a file, you can write a program in binary which converts the symbols in that file into binary code, which can be executed, which, of course, was the invention of first-generation compilers, right? At the moment, we're on the fourth generation of compilers. So after pre-processing, there is a process called type checking. Now, type checking is, if your program has a lot of errors, type checking is probably the first point at which you will encounter errors. Type checking includes things like, I have an integer variable, I'm trying to assign a string to it, right? The type checker can go through and it basically has a bunch of rewriting rules where it substitutes things for the data type, and certain combinations of data types are allowed and not allowed, and it has rules about what's allowed and what's not allowed. It crunches through the whole program without needing any particular input, right? And then it tells you, this is a way of screening the program for large classes of errors, which is why it's, well, actually, type checking, you have to be parsing first. But type checking, right? It'll tell you if you're using, it'll tell you certain things about whether your program has been composed correctly. I actually missed a step because I got too excited about CRTs. There's a step in the middle here, which is parsing. So when you parse a file, what you do is you take it and you break it down into tokens, and you arrange those tokens into what's called an abstract syntax tree. So if I take a sort of ordinary average statement like x is equal to y plus 3, right? This breaks down into a syntax tree as the top level operation I'm performing is assignment. The operands for that are x and the result of addition as applied to y and 3, right? So you can kind of see how these things will crunch together to, you go down to the extremity of the tree, solve this, substitute the answer this produces for the node, and then work your way up the tree that way. And that's how calculation actually works, right? But before you actually do the calculation, you must break it down into its component symbols, right? So if parsing fails, you get a thing I'm sure everybody's gotten plenty of, a syntax error. Syntax errors are essentially errors in the grammatical construction of the program. People don't usually think of a programming language as having a grammar because people think, well, English has grammar, pick your natural language, that language has grammar, rules of grammar. Programming languages also have rules of grammar, right? But it's something like you have to end every line with a semicolon, right? That's a rule of grammar inside of a programming language. So if you violate the rules of grammar, what you are essentially doing is preventing, basically you've caused a fatal problem in the breaking down of the program into its syntax tree, right? That's why the program fails, right? Making sense? So, after type checking, we begin the next phase in the process, which is assembly. During assembly, each of these individual operations is substituted for a sequence of machine code instructions, right? So it's possible to go through this in order, according to rules of precedent, right? If you have something like y plus 3 plus z, right? We know that y plus 3 will be executed before the result of that plus z. So in terms of the abstract syntax tree, it actually breaks down that way. You have, at the top level, this one, right? Z, then another plus down here, y and 3. You go to the extremity of the tree first, execute that first, right? And then you work your way back up the tree that way. But this itself is a machine code operation for load the value in the register that you have named y, right? So the register or memory address. So each of these correspond to a certain number of machine code instructions, right? Now, it so happens that no matter how good your compiler is, you will generate, automatic generation will always produce more instructions than a competent assembly programmer, that is to say a human, would, right? Each one of these instructions takes one CPU clock cycle in order to execute. Well, at least one, right? So basically, the amount of time it takes to execute your program, excluding loops, right, is the number of lines of code, the number of assembly lines of code. Now, in high-level languages like C#, one line can contain a large number of assembly code instructions, right? And no matter how good the compiler is, and the compilers are always pretty dang good, right? A competent human can always find ways to nip and tuck that the compiler didn't think of, because human beings are better than computers, right? So that's why you can actually, if you study and learn assembly programming, there are jobs out there, right? One of the applications that they hire assembly programmers for is actually cell phones. So the more instructions your program takes, the more battery power it takes to run your program, right? Not only does it, like memory, it takes up more space on the phone, but it also uses more power. Critically, it uses more power, right? So, you may notice, if you've got YouTube running, right, on your phone, versus some other video app service, right? YouTube's power consumption is really good in comparison to pretty much any other video app, right? It particularly trying to run it through a browser, right? The reason is YouTube has been optimized way down at the assembly code level, whereas a lot of those other ones haven't, right? So, does that make sense? So, assembly, we then have the process, so after assembly, and I'm abbreviating the process a little bit. So the end product of assembly is your machine code, right? So once the machine code has been produced, that is a file on your computer. You do not have to recompile the code every time you want to run it. Otherwise, it would take way too long to do anything, right? So and this is only true because we're talking about compiled languages versus interpreted languages, right? Interpreted languages are a bit of a different beast, but fortunately, C# is a compiled language, so this is how it works. So when you execute the machine code, there are two main things that happen, right? The first part is called linking. And no, this isn't a Zelda reference. So with machine code instructions, very often your program will need some pieces of code from the operating system, right? Minimally, you'll probably be loading standard libraries on input and output, probably a few other libraries as well. C# itself has a whole whack of libraries that it loads just by default, and it doesn't even tell you, right? You know in Unity where it says like using Unity engine? That's making reference to other compiled files. So before it executes your machine code, it must go out and find the code that it references, right? So like in the case of Unity code, if it's using Unity engine, the way that it works in Windows is this is the purpose of the DLL file. You know what DLL stands for? Dynamically linked library, right? So we link to our, stuff that's in the kernel or our dynamically linked libraries because that code is necessary for the execution, right? Then, and only then, can we actually execute the code. So basically, if I draw a line here, everything up here is static. Everything down here is dynamic. Right? The static processes only need to occur once unless you change the program source code. Right? The dynamic processes execute every time the program runs, right? So another way of saying this is compile time and run time, right? So when we talk about exceptions, I could get back to exceptions. Exceptions are runtime errors, right? So things which, so the sorts of things which are excluded from consideration are things like syntax errors and type checker errors, right? These are not exceptions. These will show up before your program even, before your program even considers being executed, right? Runtime errors show up during execution. In theory, if you move the file it's looking for and it can't find it, it may fail on linking. And that is also a kind of runtime error, but normally we don't have to worry about that with modern systems. But many things can be runtime errors. These are errors that the compiler did not have the ability to foresee, which usually means they are related to the input provided to the program at runtime. Because the compiler just compiles the program, it doesn't know what the input's going to be to your function, right? It just compiles your function for you. The compiler does not run your code. You run your code when you run it, right? So there are some things that will only pop up when it runs, right? So there's a famous example of an exception, which is kind of traditionally an exception. let me ask you a mathematical question. Right? What is the value of the following expression? What is the value of 5 divided by 0? In a computer, yes, but in mathematics, what is it? It's not 0. You're thinking about the other way around. This is 0. So let me put it to you this way. If I have 5 apples and I am dividing it into no groups, how many apples does each group that doesn't exist get? The answer is infinity. Right? So, and the reason that this is the answer to this is infinity is like if you take 5 and you divide it by 1, you get 5. If you take 5 and you divide it by 0.1, you get 50. Right? 5 divided by 0.01, 500. So basically, if you were to take that and graph it, right? As if this is x and this is 5 divided by x, right? As you approach the origin, right? This value shoots off to infinity, and in fact, coming on the other side, it does the same with negative infinity, right? Now, the actual value of this at the point 0 itself, technically undefined, right? But basically, if you approach 0 from the positive side, you will be approaching infinity. If you approach 0 from the negative side, you will be approaching negative infinity. So, in general, it's taken as true that if you divide something by 0, you get either infinity or something that tends toward infinity, depending on how accurate your 0 is, right? So, in computers, this is a problem, right? A computer cannot do that, right? Computers are finite. They only have so much memory space. Even an integer, right? Integers cannot be represented past their bit size, right? Even if it's an unsigned integer, the size of the integer is 2 to the power of the number of bits in the integer. Even if that's large, it's certainly not infinity, right? So there is some kind of effective cutoff, right? There's some effective cutoff beyond which the computer fails to be able to produce the number, right? So what does it do? It terminates your program. That's what its response is. If this is a very, very old, this is like an ancient decision, which may or may not have been the correct way to handle it, but it has been carried forward from the ancient days of computing. That if you attempt to enter this region, it'll just terminate your program. Your program will end, right? So this is what's known as the zero division error, right? Zero division error. So pretty much every CPU using at least standard CPU architecture they all behave like this, right? So if you do this in a lower level language, basically what happens, what that actually means is the CPU raises a flag that says, I haven't encountered a zero division error. It stops executing the program and it waits until somebody tells it what to do about the flag, right? Now, introducing operating systems, right? The operating system might say, okay, you can kill the process, but leave my operating system running, please, right? So, because, back in the day, it would have crashed the computer outright. But with operating systems, the operating system is, one of its purposes is to handle errors that the CPU encounters like that in such a way that the computer itself does not crash, right? And it's, they've been generally improving in effectiveness of that as time goes on. Computers in the 90s used to crash all the time. And it took a long time to boot them too. It's a wonder anybody got anything done, So more modern programming languages have a mechanism for dealing with exceptions. It's called exception handling because programmers are very original in their naming conventions, right? It's preferable if it says what it does rather than have a fancy name. So modern programming languages have exception handling mechanisms, which when something like this occurs in the programming, rather than have the error fall all the way through to the CPU immediately, and then have that error handled by the operating system, resulting in the crash of the program, it does that checking itself, right? If the zero division exception occurs, if zero division is attempted, the program will throw a zero division exception, right? Now, exceptions are, they have interesting properties. They are stack smashers, right? So you have another sort of thing inside the computer which controls the execution of functions called the system call stack. So you have the system call stack. If I have a function, say I have a function foo that calls a function bar, right? The first thing that will be put on the stack is foo. So foo then calls bar. Bar goes on the stack, right? You're now on this stack layer. Once bar finishes, it's removed from the stack, and you're back in foo. And that's how the system call stack works, right? Now, when an exception happens, let's say you had a whole bunch of functions that had all called each other, A, B, C, and D. If an exception happens in D, it will smash its way back through the stack to find something to catch it, something to catch the exception. So it will terminate D immediately, the exception will. It will then enter C and check to see if C is looking for exceptions. If C is not looking for exceptions, it will smash through C as well. It will remove C from the stack, and it will go one level higher to B and see if B is looking for exceptions. If B is not looking for exceptions, then it smashes through one layer higher to A, If A is not looking for exceptions, it will smash through to foo. Eventually it arrives at the program itself, right? If it arrives at the program itself without any function having dealt with the error, the function itself terminates, right? It's fatal exception, my program has ended, thank you for coming, go away, right? So, for example, if I have just a bare, console app and I attempt zero division and there's nothing catching it, right? It doesn't matter what layer I am in terms of function calls, that program is dead, right? So, the question then becomes, how do we go about catching exceptions, right? Well, there is a code construct called a try-catch. Like that. So, if an error occurs, if an exception occurs, during the execution of a try block, that block is immediately executed, and whatever has been placed in catch will execute at that point. Try will exit, catch will execute. It will also stop a stack smash, because the error has now been handled, at least according to, whether you actually handled the error or swept it under the rug, that's between you and your program. But as far as the program is concerned, if it's been caught, then it's been dealt with, right? So, shall we take a look at an example then? Does this make sense? Are there any questions about this? No? There we go. So, first, let us produce an exception. So, it's not quite so simple as this, right? The compiler can tell that I'm about to divide by 0 because I gave it an actual literal 0, right? However, if I replace that with some information taken from the user, it can't predict information that I give it while it's running, right? That's past the point of static compilation. So, if I say int response is equal to console.read line console.write line be careful not Stack Overflow every time. Int 32 parse. Okay. Int 32 dot parse. There we go. Response, there we go. All right, let's run. Thank you. So, be careful not to enter 0, okay? 5. Yay, it worked. Now, if I'm a naughty, naughty boy, and I enter 0, exception unhandled, system dot divide by 0, exception attempted to divide by 0. And you can see that this thing's like frozen, kind of. Yeah, that's frozen now. The program has officially crashed. Can I even close the window? There we go. Yep, it closes. So, that is an exception, right? So now, let us handle the exception. Try this, catch that. So, on success, we'll say something like, oh good, something other than 0. And if the exception occurs, we say something like, oh my blessed aunt, you're a cheeky little programmer, aren't you? So, if we enter something that's not going to cause a 0 with an error, like 6, oh good, something other than 0. If we execute, if we enter a 0, we get, oh my blessed aunt, you are a cheeky programmer, aren't you? There you go. So, but notice, here's the important point, right? Notice that okay. Notice that the print statement inside of the try block didn't execute here, right? Because as soon as the error is encountered inside of the try block, execution finishes, terminates, it's done, it's gone, it's no longer applicable. You jump immediately to the catch case. You don't even finish the line that you're on, right? So, for example, I can demonstrate that. Let's declare int up here, int x up here, right? We are saying, let's say that int x is 10 initially, then it's 5 divided by response. Then if we console.writeLine x afterwards, If we enter something that's non-zero, 0 is the response because like 0 divided by 1010 is very close to 0, at least close enough that you would need a float for it, right? Whereas if you enter 0, you will notice that the value of x is 10. 10 is retained, right? That's because the 0 division terminates before the assignment is performed, which makes sense. Why would you want to write an error into x? You might need x later, right? Does that make sense? They're not too terribly complicated try-catches. In fact, they don't get much more complicated than this, except for the fact that you can raise your own custom exceptions. They're quite a bit like if statements, except the condition is an exception happens inside of this block. Does that make sense? So far, so good? All right. So let's talk about some different types of exceptions that you can encounter when doing C# programming, right? Slight pause while I bring up a list. List of C# exceptions. We probably don't need the complete list, but this will be fine. I'll pick out ones that are like interesting. So divide by 0 exception is something we just did. You'll notice that there's also a DLL not found exception. You remember what I said that linking shows up as a runtime error? Well, this would be an error with linking. I described exactly that. Index out of range exception is one that will be one that you probably encountered at least once when you were doing assignment 1. The exception that is thrown, this is the exception that is thrown when an attempt is made to access an element of an array or collection with an index that is outside its bounds. That is to say, you have an array of size 10 and you try to access element 20, right? It doesn't work. The program crashes. You get an index out of bounds exception, right? Now, it's always like, it's not good to rely on exception handling to fix your buggy code for you, right? If your loop is prone to index out of bounds exceptions, you should fix the loop and not use this, right? But this is I have given you the tools you need to handle it if you need to. So index out of bounds, or index out of range exception. Insufficient memory exception, basically, if you're trying to create a data structure and your computer memory is already full, very, very, very rare these days. But that's the exception that's thrown. Almost impossible to predict, almost impossible to do anything about. I would say in this case, the correct response is to crash the program, right? By the way, interesting point about memory. So you know RAM, right? Do you know what happens when you run out of RAM? Well, it's not that there's no more memory, it's that there's no more RAM. And I just gave you a hint. If it completely fills up the RAM, what does it do? No, it doesn't overwrite previous stuff. It starts using the hard disk, right? This is called caching, actually. So basically, this is what happens when your computer runs out of RAM, right? It takes a region of your hard disk and it says, okay, this is my RAM now. This is me, this is RAM. The hard disk is like, oh, I'm not RAM actually. It's like, I don't care, you are RAM now, I need RAM and you are it. But I'm much, much slower than actual RAM. I don't care, I don't want to crash, I need the memory, you are my memory now. That's what the operating system says to the hard disk. And the hard disk is like, well, okay, I'll do what you say, but just so you know, this is going to make you really slow. So this used to be a thing with Windows that was quite noticeable in back in the Windows Vista, Windows 7 kind of era. Do you ever notice Windows really wants to be reset every few days? You know, you want to know why Windows wants to be reset every few days? Windows suffers from a problem called memory leakage, right? So basically what a memory leak is when a program gives itself memory, but then it never gives it back, right? So inside of your RAM, you'll have all of these sectors that are given over to programs that never returned them when they were finished with them. So over time, the RAM just kind of fills up with dead, they're still electrically live, but they don't point to any program, right? So it fills up with all of these dead cells, right? Cells that aren't useful.
Is this the one in the Windows? Is this the app data, the local app data?
Sorry, say that again?
Is it the app data, local app data? Is that the actual?
No. It wouldn't show up in your file system. Yeah. Sometimes they do it in a separate partition. Not all of the partitions on your disk are actually visible to you. There's a boot partition on your drive that, generally Windows doesn't even show you that it's there. You have to go into the command line interface and mount the drive in order to be able to see the contents, which I don't recommend because I don't recommend anybody mess up their boot sector. Because if you mess up your boot sector, you have to reinstall your operating system, right? Because it won't boot. Basically you have to knock it back to BIOS, right? You guys know what BIOS is? Oh my goodness. I just realized you guys probably don't know what BIOS is. Are these things actually on? Can I turn this off? Gather around. Come here. So I have to force a hard power cycle on this.
Oh, it's really to press it for that.
That's the one. Let's see here. If somebody from IT comes, we didn't do anything. Okay. There we go. Monitor is on, but I just pulled the power cable on the computer, so I put it back in, quickly run around. F2 or F11 is usually up. BIOS on this one locked. If it is, I'll show you on the laptop. Will you work? I think not. I think this is working out. Okay. That's okay. I'll show you on the laptop. That computer might be IT now. We'll see. I'm a little nicer to mine than the lab computer. I'll just, I'll exit it gracefully, turn its power off properly. Did that thing actually come back on? So don't pull the power cables. I'll just say I tripped. I tripped again and fell against the power cable. Okay. So.